everybody, and welcome back. For our next topic, today we're going to take a look at something called optimization. So up to this point in Unit 3, we've spent the whole unit learning different ways to apply derivatives and being able to describe when different functions or quantities are at their maximum or minimum values. So that information can be easily applied to really any real-life quantity that we would want to know when it reaches its own minimum or maximum value. So this process relates to many different real-life scenarios, including business and engineering. So what we're going to do today is we're going to take a look at how a specific quantity changes with respect to other quantities that are used as input values within that same situation. And we have to keep in mind that our ultimate goal is to optimize. So that means the optimization process is very common in packaging. If you think about Amazon, they want to optimize the time spent and money and resources spent on delivering packages. So that means driver routes, you want to optimize or minimize the distance and time, and then fuel spent driving those routes so that they can maximize their profits. So there's all different kinds of scenarios where this process of optimization can be used. So it's a pretty simple process as far as the calculus involved. It's really just a matter of kind of taking the time to set up. This is a similar process to our related rates problems in the previous unit, where we had to kind of gather all the information, all the parts that we had to work with. And then once we had all that, the calculus part of it wasn't too bad. So why don't we dive in here and try one of these. So a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. So we want to know what dimensions will produce a box with maximum volume. So this is actually a very common real-world problem. Not that every person walks around every day doing this kind of math problem, but there are actual people whose job at some of these packaging or distribution companies, their job is to maximize the amount of space that a package has while minimizing or working with constraints on how much materials, cardboard, you have to actually design the box. So this is a very common thing that some engineers go through or work with. So in every one of these problems, we are going to have what we're going to refer to as a primary equation. So our primary equation is the quantity that we want to optimize. So we're looking for language that talks about maximum of something or minimum of something. So in this case, we are trying to find dimensions that maximizes volume. So in particular, this is the volume of a box or a prism, a rectangular prism. So volume of a rectangular prism, the formula for that is length times width times height. So we've got a box. I highly recommend that you guys always try and sketch some kind of diagram, no matter how good of an artist you are. I promise you that I am a very bad artist, but I'm still going to attempt to visualize all the information or stuff that we know. And actually, I already did a really bad job of this because it's supposed to have a square base. So let me try this again. So it having a square base, what we don't know though is the height. So if the base is a square, then so is the top. But it could be really tall, it could be really short. That part we don't really know. But we do know for sure that the base is a square. And why that's important to us is when labeling these dimensions. Now, the general formula is length times width times height. So we're going to start with something like that, but then we're going to dive in and actually come up with good or better ways to represent those dimensions so that they're not all different variables. So for example, in this case, if we know that the base is a square, that means that two of these dimensions are the same thing. So I'm going to label those as x, and that's an arbitrary choice. You could really label them as anything that you want to. But then this third dimension is the thing that we're not really sure how it relates to the other. So because it could have a different value, we're going to label it with a different variable. So knowing all of that, now we can write another form of this same primary equation, x times y, or x squared y. So that's our primary equation. That's the thing that we're going to try and maximize. Now, the big difference between optimization and related rates problems is related rates, you are always looking at how quantities change with respect to time. These problems have no aspect of time whatsoever. So we can't just take the derivative to any variable that we want to. We want to look at how we can maximize the volume, and that volume has to only depend on one variable, or we can't do this yet. So because this primary equation right now has two input variables, both x and y, we need to use a secondary equation. So the secondary equation's job is to relate all of these variables in some other way so that we can try to solve for one and then take that expression and substitute it into our primary so that this guy only has one input variable. So that's our ultimate goal. We can't do calculus until the primary is one quantity that is defined as a function of just one other variable. So right now, v is a function of x and y. We want it to just be a function of x or just a function of y. So that's why they gave you this other information. So if the engineer's job is to maximize volume, if you don't give him any kind of constraints to work in, then he can't really answer that problem because the maximum volume would just be the biggest possible box that you could possibly make. But in this case, the extra conditions or extra constraints are that we want it to be an open box. So an open box means normally a prism has 6 sides. So we would have 4 faces that look like this guy, so all the way around, and then the top and the bottom. But in this case, we only have 5 faces because it's an open box. So we have 4 of this kind, and then we'll only have 1 that is a square on bottom. So talking about the surface area, they've told us that we essentially have 108 square inches of cardboard. So we need to calculate or come up with an equation that can calculate that surface area. So for right now, I'm just going to say surface area equals, and then we basically just have to find the total area of all these things. So we said we have 4 of these rectangles, and each rectangle has an x dimension on one side and a y on the other. So that area would be 4xy. Plus, then this one square side on the bottom has dimensions x by x, so it has an area of x squared. So they told us a value for this. So again, if we didn't have this number, then we would be in the same boat with the secondary equation that we are with the primary. So I have to have a number for at least one of these variables to go in there. Otherwise, I couldn't do what I need to do. So I'm going to rewrite this as 108 equals 4xy plus x squared. So from there, my job now is to pick one of those variables, either the x or the y. Technically, it does not matter which one we do, but you do want to put a little bit of forethought into this. If I wanted to try and solve this equation for x so that I end up with x equals something in terms of y, that would prove to be really difficult and sometimes might not even be possible because there are 2 different degrees of x in this equation. So in this case, we actually wouldn't be able to solve for just x and have just a function of y. So in that case, we don't really have a choice. We have to try and isolate the other variable. Now, there will be times where you could do either or, and in that case, it still doesn't actually matter which one. If it's possible to do it for either, then it really doesn't matter. In this case, it's not possible, so we have to try and isolate y. So to do that, we're going to move the x squared term over and then divide everything by 4x. So that would end up giving us an expression, 108 minus x squared. Sorry, I didn't like that my circles weren't touching there for the 8. So 108 minus x squared, and then all divided by 4x. So that is what the quantity of y is equal to. So what we can do now is that now that we have a secondary equation that is isolated for one variable in terms of the other, now I can just take this guy and substitute him into the primary equation. So if we think about what's going on, right now I have an equation for volume. Volume depends on both x and y's values. But we found a relationship between x and y that shows that y's value could really be represented or depend on the value of x. So because of that, it's kind of like a chain reaction. Now we're saying that v really could just depend on the value of x if I make this substitution. So that's what we want to do. So when we do that, now we would have a function of just x, and we could take the derivative with respect to that input variable. So if I do that, we would end up with x squared times this fraction. I'm sorry, not 4x, x squared on top. So times 108 minus x squared times 4, or divided by 4x. And now we just, again, always want to do algebra to start before we get to the calculus. So I'm just going to reduce this guy and simplify it as much as I can. So we're going to do a couple things here. We've got a factor of x on top and bottom, so one of these cancels out with that guy. So let's go ahead and distribute the x inside. So if I send that to the numerator only, because again, it's just like the tops are multiplying, that would give me 108x minus x cubed all over 4. And then this is another situation, I don't need to keep this as a fraction anymore. I can split and reduce this. So I would get 108 divided by 4 is 27x. So all right, it's going to be another one of those days with my tablet. 27x minus 1/4 x cubed. That is our new form of our primary equation. So before, to calculate the volume, I would have to know an x and a y value. Well, to find the y value, I'd have to plug a value of x into this y equation, get that number, then plug it back in here. Now we're just skipping over all of that, and now we could just plug one value of x into the volume equation, and we get the same answer, just with fewer steps. So it's at this point that now we are ready to do our calculus. Now I can take the derivative as, or with respect to x, of everything in here. That result gives me the change in volume with respect to the change in x equals 27x, and this is, we're just taking the derivative like normal. Again, it's not exactly like those related rates problems, because those, we produce those extra rates of change. This one, it's really just regular old derivatives, no chain rule because of the dt. So in this case, 27x is just 27. 1/4 x cubed would turn into 3/4 x squared. So now our job is to do all of the analysis of minimums and maximums and our relative extrema that we did for all these other functions within this unit. So this is my derivative. So now I want to try and maximize. Again, our goal is to maximize this equation. So if I want to maximize that equation, we are looking for where does the function of volume have that local maximum. And our options here are really whatever we want to do. So I have the first derivative test in my toolbox. I also have the second derivative test. If it's my personal choice, my personal preference is to do the second derivative test as much as possible. I think that it's actually much easier to do that most of the time than the first derivative test. So no matter what we do, we're going to have to find critical numbers. So we're going to set our derivative equal to 0. So if this guy equaled 0, that would yield, I'm going to move the x squared over, so we would get 27. Tablet really does not want to cooperate. 27 equals 3/4 of x squared. I'm going to multiply both sides by 4/3 to get rid of that coefficient. 27 divided by 3 is 9, times 4 is 36. So 36 equals x squared, or x equals plus or minus 6. Now, because of the real world context, sometimes we're going to have extraneous solutions or values that really do make this equation equal to 0, but don't make sense in the context of the problem. So in this case, I'm ignoring the negative value of, or the value of -6, because that can't possibly be a dimension for this box. Now, we only ended up with one critical number, so some people may just assume automatically that guarantees that this turns into a relative maximum. That is not always the case. It's not safe for us to just assume that. So we do still need to do some extra work to guarantee that this is the dimension of or value of x that will produce a maximum volume. So this is just a critical number. So now our options are either check increasing and decreasing intervals using the first derivative test, or what I'm going to do is use the second derivative test and check the concavity. We know on this, on the volume equation, m equals 0 at x equals 6. Now I need to just make sure that we have negative concavity. So I'm going to find d2v dx2 by taking the derivative of this guy. So derivative of 27 is 0. Negative 3/4 x squared would turn into negative 6/4 or negative 3/2 x. And now I can complete our little simple second derivative chart. Remember, this is just where we take the critical number where the slope was equal to 0 and we substitute it into the second derivative. So negative number times positive 6 would give me a negative, so concave down. So putting all of that together means we do have a relative maximum at x equals 6. But remember, the problem is not just asking for one dimension. We want to know all the dimensions of the box. So we have the x-coordinate. Now we need to go back to our secondary equation. So this will always be kind of a full circle kind of thing where we use this box to start the problem, and then we come back to it at the very end. So to find the y-coordinate, then we would get y equals 108 minus 6 squared is 36. And then divided by 4 times 6 is 24. So let's see. So we get 108 minus 36, that's 72. Divided by 24 gives us 3. So for the dimensions that will produce a box with a maximum volume, if we only have 108 square inches to make it with an open top, then those dimensions would be, in this case, we are using square inches for area, so then each single dimension has just inches. So this would be a 6-inch by 6-inch by 3-inch box. All right, so let's try to take a look at this next one here. So this one says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. So let's do a little bit of artwork here. So there's my river. Pretend like I actually drew that straight. I was trying my best. So because the river's there, he's not going to put fence up along that. So we really only have 3 sides to this rectangular field. So again, all these problems, we can kind of use any arbitrary variables that we want to. It's your choice. I just kind of like to be consistent. Anything I draw horizontally, I'll use X, and then vertical, I'll use Y. So then if we've got 2,400 feet of fencing, he, again, needs no fence along the river. We want to know the dimensions of the field that has the largest area. So it's not exactly the same language as before, but largest, same idea as maximizing. So area then becomes the quantity that we are trying to maximize, or remember, we refer to these as our primary. So the primary equation for this rectangular field would be area equals dimension times dimension, or in this case, x times y. So now, once again, just like the previous example, we don't know which variable to take the derivative with respect to because there are 2 inputs that area depends on. So this is where we need a secondary equation. And again, the secondary equation, there's not really any wording in here that will kind of point you in the right direction always. Sometimes you have to think a little bit deeper about the information that's actually present. But the idea of the secondary equation is it's just some other way that expresses a relationship between all of these input variables so that we can solve for one and replace in the primary. So in this case, the other piece of information that we know about is this footage of fencing. So fencing is like the distance around. So this is like the idea of perimeter. So in this case, the total distance around that field that needs to be fenced in is equal to 1x plus 2y. And again, 99% of the time, it would be really difficult to make one of these problems without this. There's some kind of extra number given to you in the problem, and that value is what we are going to use in this secondary equation. So we can rewrite this as 2,400, which is the constant known value for total perimeter. That's how much fencing we have to work with. So now we can choose to solve for either x or y, and in this case, the first equation, we didn't have the option. We couldn't solve for either of them, so we were kind of stuck with which one we had to isolate. In this case, you can solve for x or y. Both are possible, It is a little bit easier to isolate x, though, because all we have to do is just move this term over. So that would be my suggestion. So if we solve for x, then we get 2400 minus 2y. And again, you wouldn't get it wrong if you tried to solve for y, just more steps, one extra step, so it's a little bit more difficult. But in this case, solving for x allows me now to take this quantity and substitute it into our primary equation. So that yields 2400 minus 2y times y. So when I distribute, we get area is equal to 2400y minus 2y squared. Now we have a primary equation for the quantity we're trying to optimize, area, that depends on one input variable. So now we can take the derivative with respect to that variable. So this is going to look a little weird for this one. So I'm going to take the derivative of that equation with respect to y. This is the first time we've written that out. But it's always relative to what the input variable ends up being. So in this case, I end up getting dA dy equals derivative of 2400y would just be 2400. Again, we don't end up with extra rates of change here because the variables match up. Equals 2y squared would turn into 4y. So that is my derivative equation, the change in area with respect to the change in the y dimension. And now we can find our critical numbers. So we got 0 equals 2400 minus 4y, or 4y equals 2400, which gives me y equals 600. So just like with the previous one, technically, or not technically, it just so happens that we only end up with one critical number, but it's still not safe for you to just automatically assume that this yields a maximum in that area. We still want to do the legwork to prove that this is in fact true, okay? Now for this one, the last one we used the second derivative test. I still always think that's going to be easiest. Really the only time that might not be the best choice is if finding the second derivative, you can tell by looking at the first derivative that it's going to be really time consuming and difficult and lots of opportunities for mistakes. But in this case, our first derivative is a linear function, which means the second derivative is a constant. So this one is definitely a no-brainer. Find your second derivative. And when I do that, we end up with 2400 is a constant, disappears. This leaves me with just -4. And -4 is a constant value, which is always going to be negative. So if this guy is less than 0 for all values of x, or excuse me, for all values of y, this is a fancy little symbol used in proof writing for mathematics. It stands for the phrase for all. Just a nice little easy way to shorten up some of the writing that we have to do. But if this is true for all values of y, that means we don't even have to worry about testing any critical numbers or anything. We know that the area function will always be concave down for the entire graph, which makes sense because the original is a quadratic with a negative leading coefficient. So we kind of already knew that without having to do the calculus, but still good to prove it with the calculus so that we get the repetition with this. So knowing all of that, we know that it's concave down, we know that there is 0 slope, so we know that when y equals 600, this is in fact a relative maximum. But if we want both dimensions, not just one of them, we got to go back to our boxed in form for the secondary, and again, we'll substitute that 600 in there. So if y equals 600 is part of the solution, and x is equal to 2400 minus 2 times that y value, then we would get 2400 minus 1200, or 1200 for that x coordinate, or that x dimension. So the dimensions of the field that maximize the area would be 600 feet by 1200 feet. So again, all of these optimization problems are going to follow a similar format. We're going to identify our primary, then we're going to identify our secondary using this extra piece, or this extra value, extra piece of information. We're going to isolate one of the values, or excuse me, one of the variables in our secondary, and use that to rewrite the primary as a function that depends on just one type of variable. Once we've simplified that, then we'll do our calculus to find our derivative, and then our critical numbers. And then from there, we can decide if I want to do the first derivative test or the second derivative test to identify any relative extrema. And then we can work backwards and find all the dimensions or whatever values of x, y, whatever the variables are that we need to find for the problem. All right, now for our next example, this one's always a good one. So this one says a rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the left and right margins are to be 1 inch. So we already have kind of a diagram over here, but just to kind of highlight what's going on here. So I've got an outer rectangle and then an inner rectangle. So that inner rectangle is the print size. So it says a rectangular page is to contain 24 square inches of print. So that is referring to this inner rectangle. So the diagram is already labeled for us. This inner guy, whoops, now I don't know, this is straight out of a textbook. I don't know what genius decided to make the vertical side X and the horizontal side Y. And actually, you know what? I'm going to change that because that's going to drive me nuts. This whole problem. So that's X, that's now Y. Make the changes on your page as well. So we've got dimensions for the inner rectangle are X and Y, but then to build the dimensions for the outer rectangle, we have to take into account the borders on both sides, or the margins. So a 1 inch border or margin on left and right sides means this whole thing has dimensions X plus 2 across the bottom. And then 1.5 inch margins on top and bottom make this side Y plus 3. So we do have to be careful here because both of these are rectangles, but you have to be careful which one we are trying to maximize or minimize. So in this case, we're looking for the dimensions of the page so that the least amount of paper is used. So the paper is the outer rectangle. So that's the quantity that we are looking to minimize. So our primary equation is area of a rectangle, so that would be base times height. But in particular, our base is X plus 2, and our height is Y plus 3. So again, our primary quantity that we're trying to optimize depends on two different input variables. So we need a secondary equation. So a secondary relationship that relates X and Y together with some additional quantity that we know about that allows us to actually solve for X or Y. So that's where the inner area comes into play. So rectangular page, we know it's supposed to have 24 square inches of print. So we don't care like exactly the dimensions of the inside. We're just needing to find what they would need to be so that the borders and everything minimize the amount of paper. So that means for the inner rectangle, this inside area is equal to just dimensions X, Y, because we don't have any borders for that part. And then they told us that that area is always going to be 24 square inches, no matter what. So now, again, we have a secondary relationship. The only variables in this equation are X and Y, which allows us to solve for one or the other. And again, in this case, we can solve for either. It takes the exact same amount of steps. So it really is just a personal preference. I like to work with X's more than Y, so I'm going to choose to solve this equation for Y so that I can replace Y in the other equation. But again, it really doesn't matter. It's the same amount of steps either way. We're going to divide by a variable. So we know that Y is equal to 24 over X. So that is what we are going to substitute in for Y in the primary equation. So doing that is going to give us area equals X plus 2 times 24 over X plus 3. Now, if we stop there with our algebra stuff and start to do calculus, we would have to start a product rule. But because these are all polynomial or power terms, we don't have to do that. We could choose to just multiply this expression the whole way out and then just do power rules. So that's what we're going to do. So this one's a little trickier, though, because of this rational function in that first term, but we can still accomplish it. We just have to think a little bit carefully, or can set up a quick little box rule. It works even with these ugly looking things. So 24 over X and 3. So X times 24 over X, that would just be 24. And then we got 3X 2 times 24 over x would be 48 over x, and then 2 times 3 is 6. So that means we have common terms there that I can combine. So we'll have 30 plus 3x plus 48 over x. I'm going to go ahead and just rewrite that as x to the negative first. That way it's ready for me to do our calculus. So now we can take the derivative of this guy with respect to x, because that's my input variable. So the change in area with respect to the change in x. Tablet still does not want to cooperate. We get 30 as a constant, drops out. Derivative of 3x is 3. And then 48x to the negative first becomes negative 48x to the negative second, or 3 minus 48 over x squared. So there's our derivative. Now we will find our critical numbers. So critical numbers, again, are where x equals 0 or undefined. So in this case, we know that one critical number would be where x equals 0, because that would make the derivative undefined. But again, just because we follow the same steps as always doesn't mean that every value results in a real life scenario. In this case, x equaling 0 means that there would be no text on the inner part of this page. So we know that that's not a value worth exploring, okay? But there is another solution. So we're going to set this guy equal to 0. I'm going to move this term over here. So I would get 3 equals 48 over x squared. This is really 3 over 1. So now I can exchange on these diagonals and preserve, whoa, I don't know what happened there. Preserve the value of this equation. So we would end up with x squared equals 48 divided by 3, or 16. Then I can square root both sides, and I get plus or minus 4. But again, just like 0 not making any sense in the real-world context, this inner dimension being negative 4 also does not make any sense. So we are really just working with positive 4 as our critical number. And again, in this case, we are not just going to assume that this automatically does what we need it to be. Let's go ahead and prove that it does. So again, looking at my first derivative, this is not a difficult function to take the find the second derivative for. So I'm just going to use second derivative test. So let's do that up here where I've actually got some space. So we get d2a dx2, 3's derivative is 0. And negative 48x to the negative second would become positive 96x to the negative third, or 96 over x cubed. So if I were to plug positive 4 into our second derivative here, positive divided by a positive is a positive. So we have positive concavity, or concave up. So that paired with 0 slope does in fact yield a relative minimum for us, which is what we were hoping for. Again, we were trying to find the dimensions that used the least amount of paper. So we're trying to be as conservative here as possible. So x is 4 is a part of this solution, but again, we want both dimensions. So I'm going to take this back to our secondary equation. Y is equal to 24 over that x value, or 6. So the dimensions of the page, so you do have to be a little careful here. So 4 by 6 would be the dimensions of the inner portion of the text only. So to find the dimensions of the page, we would need to go back to the original primary equation. The base dimension is x plus 2, so that would be 6 inches. And then the height is y plus 3, so 6 plus 3 gives us 9 inches. So if we had a piece of paper 6 inches by 9 inches with the borders that they desired, we would be meeting the needs for the area of the print, but minimizing the amount of paper needed to create this page. All right, so now for our last one, we're going to step things up a little bit. This one is definitely going to be a tough one.
No, God! No, God, please, no! 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 No!
So this one, what makes this one pretty tough is the calculus involved, finding these derivatives. It's going to be pretty tricky, but bear with me, follow along. It's not like, this is not a kind of problem that you guys would most likely have to do 100% independently on your own. But if you can follow along with me and make sense of all the steps that I'm doing, then you should be pretty well set up to do just about any other kind of problem on your own. The big thing just to take away from this is when we do these optimization problems, the structure, the process is going to be the same. Really what changes from one problem to the next is just the quantities involved, and therefore the equations that we use as our primary and our secondary. But again, the process is really going to be the same. Find a primary, find a secondary, use the secondary to solve, isolate from one input, rewrite the original primary equation in terms of just one input variable so that we can do our calculus, take our derivative, find our critical numbers, and then use all of that information to figure out where we optimize by maximizing or minimizing our original quantity. All right, so let's dive into this one. This one says two posts, one 12 feet high, the other 28 feet high, so you can see that in the diagram here, stand 30 feet apart. So that's the total distance between the base of the two poles. They are to be stayed by two wires. So that language, if you're not a farmer or you're not familiar with that or a construction worker or anything, basically just means that to stabilize both of these, we're going to take a cable and pin it in the ground in between. Okay, so attached to a single stake. So we're tying both of these wires to that same stake. So they run from ground level to the top of each post. So essentially, we've created two right triangles in this diagram. So we want to know where should the stake be placed between the two poles to use the least amount of wire. So this diagram's kind of already done a lot of the defining of the quantities for us. We're going to walk us through why they chose to do it the way that they did, okay? So first off, distance in between. So the distance between all of this is known. Okay, so the total distance is 30, but what we don't know is exactly where we're going to put the stake in between. So these actually become two distances, but they kind of relate to one another. So they decided to just name one as x, an unknown quantity, and then the other one we just calculate by taking whole minus part. So that's where we get the expression for 30 minus x. Now this one is unique because x is actually operating within an interval. So for this problem, because it's acting or coming out of a defined interval, we actually have to do this, the end of this problem slightly different than other problems. All these other ones, there's not really been a definitive interval that the values have to operate within. So the previous one, there was no limit on values for the input variable. So because of that, having this interval, we have to approach our maximizing or minimizing process at the end just slightly different when we get to that. But let's keep that part in mind, okay? So that's where the x stuff comes from. Now for the wire itself, the wire is the quantity that we are trying to minimize in this case. So for our primary, we need something about the wire to be our primary equation. So the total length of the wire, we basically are just using one wire and then we stake it down and it stabilizes both of these guys. So the total length of the wire is just these two dimensions added together. So that's why they chose to give each wire its own name, but the quantity of W equals Y plus Z is what we're adding together, and that is the primary equation that we're going to optimize. Now, the reason why each wire needs its own independent variable, though, is because they're not going to necessarily be the same size. I guess technically they could be, but that's not a guarantee. So they could be different values, so we need different variables, but also each one creates or is a part of its own independent right triangle. So we need those quantities to be separated so that we can manipulate and come up with expressions for each of these triangles. So that's where we got this primary equation from. So as of right now, W is our quantity we're trying to optimize, but right now it's depending on Y and Z. So we're going to have to do something unique here. So in this case, we actually don't have just one secondary equation, but we're actually going to have two. Because with the information that we know, there is no one way as of right now, to take the quantities of y and z and relate them to each other. But what we can do is come up with equations that y and z both relate to a third variable, x. If you noticed, x is not in the primary equation anywhere, but that's because there's relationships between x and y and x and z. So what we're actually going to do is we're going to replace y and z both in the primary equation with an expression of x. So to do that, let's analyze this first little triangle. So first little triangle has a base of x, a height of 12, and a hypotenuse of y. So by Pythagorean theorem, we have one equation that says x squared plus 12 squared, or 144, equals y squared. Then for the big triangle, we have dimensions. The base is 30 minus x, the height is 28, and the hypotenuse is z. I know I didn't draw it in the right direction, but I just don't feel like erasing it now. Still works the same way, just oriented the other direction. So for that one, we would take the base squared, so that would be the quantity or the binomial 30 minus x squared, plus 28 squared, equals that hypotenuse squared. So both of these equations have a variable and then x. So what we can do is, just with a little bit of manipulation, we could easily solve each of these for y and z and get a function of x that we can then substitute into that primary equation. That's where this gets pretty tricky, okay? Now, for the first one, I'm going to rewrite this top guy down here in blue. So to solve for y, all I have to do is square root both sides. So this one's pretty straightforward. So I'm going to flip sides just to make it a little bit easier. So I get y equals x squared, the square root of x squared plus 144. No, I cannot simplify the stuff inside, even though they're perfect squares, because it's a sum, not a product. If it was a product or a quotient, then we could do that. But in this case, it's a sum, so I can't simplify. So this one's good to go. I know what y is now equal to, so in a second, we can make a substitution here. Now for the bottom guy, it's still the same step that we just really need to square root both sides, but this stuff over here I need to do a little bit more work for. So I'm going to do that down here. So 30 minus x squared, square double square, we're just expanding this binomial, so I get 900 minus 60x plus x squared. And then plus 28 squared is 784. So then by combining these like terms, what I really end up with here is z is equal to the square root of, I'm going to put it in standard form inside, x squared minus 60x plus, combining my constants, 1684. So now I know what z is equal to. And now I can make a substitution into the primary for z. So this is just unique because we didn't have one equation that relates just y and z and some constant. So for this one, we had to use the only other information that we had, which was stuff about x. So this is another possibility. In some scenarios, we could use a third variable that both of our inputs relate to come up with two secondary equations, solve for each of our inputs, and then substitute in. So my resulting equation here now says that w is actually equal to the square root of x squared plus 144 plus the square root of x squared minus 60x plus 1684. Now we are actually ready to take the derivative of this guy. So to do that, again, it's only dependent on one variable. So taking the derivative with respect to x would give me dw dx equals, and now this is where the calculus is going to get a little tricky and complicated. So to do this, both of these guys have the form of u to the 1/2. Its derivative would be 1/2 u to the negative 1/2 times u prime, or u prime over 2u to the 1/2. Or I could write that one more way, 2 times the square root of u in that denominator. So I'm going to set up that structure for both of these, where the inside of each is our u, and then the derivative of that would be the u prime on top. So I'm going to do some mental math without having to write all of this down. And I can do that because the derivatives for these insides are pretty easy, and most of you guys are at a point now where doing that's not too confusing. So if the inside here is u, then on the bottom here, I would end up with 2 square roots of x squared plus 144. And on top would be my u prime, which in this case would be 2x. Derivative of x squared is 2x. Constant is 0. So I can actually go ahead and let's reduce out that extra factor of 2 in top and bottom. All right. Now for the second guy, it's a bigger u or bigger inside function, but the structure is still the same. It's still a square root of something. So we'll end up with 2 square roots of that something in the denominator. So I can go ahead and get that in there. And then for this inside, the derivative would be x squared turns into 2x. Negative 60x turns into negative 60. So just like with the first one, this guy also has a common factor top and bottom of 2. So I can divide the bottom by 2 and both of these guys by 2. So we end up with x minus 30. So that is my derivative. It's not nice looking, but again, the process up to this point, the process has been the same. It's just the given scenario and conditions are slightly different. All right, so next step in the process, I found my derivative, I did the calculus. Now we need to find those critical numbers. So this is going to be a little bit labor intensive here. So again, please bear with me, don't give up. I'm doing all the hard work, you guys just got to follow along. So to find those critical numbers, we want to set our derivative equation equal to 0. So when I do that, I end up with fraction plus a fraction equals 0. Well, to solve that, one method is to isolate or separate one fraction away from each other. That's going to allow me to cross multiply and wipe out all these denominators. So I'm going to do that. I'm going to keep the left fraction there. So I have x over x squared plus 144 equals, and then I'm going to move this stuff over to the other side. So right now I'm adding that fraction, which really means I'm subtracting it, but subtracting it can really mean just giving a factor of -1 to the numerator. So this was positive x, so it becomes negative x. That was negative 30, so it becomes positive 30. Let me fix that. And then denominator would still be just that radical. Okay. So now if you look here, we've got a couple things going on. So I've got fraction on both sides. So to really, the only way to solve this is to get rid of the denominators. And then I also have radicals in the equation. So one option would be get rid of the fractions first, then get rid of the radicals, or vice versa. In my opinion, it would be better to try and get rid of the radicals now before we start multiplying by stuff. If you do it the other way, then you end up with a polynomial times a radical, and when you go to get rid of the radical, that can be a little tricky and confusing. So if I want to get rid of the radicals, I really just have to square everything. I square this fraction, I square that fraction, which is really like squaring that numerator and squaring that denominator, squaring that numerator and squaring that denominator. So when I do that, I get on the left side x squared over just the inside of this radical, so x squared plus 144. No, these x squareds do not cancel each other out. I know someone's probably tempted to do that. This, if it was flipped, if I had x squared plus 144 on top and x squared on bottom, we could split and reduce, but we don't have that. Remember, multiple terms in the denominator means we can't reduce unless it's a factor of all these terms. All right, and then on the right side, the top is a binomial being squared, so we're going to do our square double square trick again, like I did over here in green. So first term squared becomes positive x squared, then we double this product, so negative 60x, and then last term squared becomes plus 900. Then the denominator, oh, whoops, actually I don't need the radical anymore because that was the whole point, and I forgot about that. The radical disappears now, so we're just left with the inside of x squared minus 60x plus 1684. Again, just because we have same terms on top and bottom doesn't mean they cancel out. Only common factors of top and bottom can be reduced. So now the radicals are gone. So now to get rid of the denominators, again, we can cross multiply. Some people don't like that term because it's misleading and it doesn't actually explain what we're doing. Essentially, we're doing two steps in one. If I want to get rid of this fraction's denominator, I would multiply both sides of the equation by x squared plus 144. If I wanted to get rid of the right side's denominator, I would multiply both sides by its denominator. We're just doing it all in one step. So when we draw these lines to cross multiply, by multiplying both sides by x squared plus 144, it cancels here on the left side, so it's gone, but then you're left multiplying this top by that factor on the other side. So that's really all we're saying here. When we draw those cross multiplying lines, you're doing a bunch of multiplication. Some things cancel out on some sides, other sides don't, so we're actually left multiplying those. So when I do that, my result, x squared times this guy, when I distribute, I would get x to the fourth minus 60x cubed plus 1684x squared equals, and then on the other side, this one's a little bit trickier, so no harm in setting up a quick little box. And these numbers are gigantic, so definitely not a bad idea to grab a calculator. You will need a calculator to do some of this multiplication, unless you are a super genius or you have the answers to the problem sitting close by. So this would give me x to the fourth negative 60x cubed, 900x squared. That one was easy. And then on the bottom, we get 144x squared. Let's see, that is negative 8,640x. And then this guy is 129,600. Again, I didn't do that in my head. I have the answer sitting nearby, so it makes it a little bit easier. Now we just combine our like terms, so I get x to the fourth minus 60x cubed plus, what is that, 1044 x squared minus 8640x, and then plus that giant constant. All right, so that's a mouthful. But now the really, really hard stuff's done. Now this just turned into a polynomial equation. And our job is to simplify this, get everything to one side, and then try to factor. And if you notice, before we start moving stuff, I have common terms on opposite sides. So I can subtract an x to the fourth term from both sides, and the equation stays balanced and true. Same thing, I can add 60x cubed to both sides because they share those common terms as well. So this went from a fourth degree polynomial to now it's just a quadratic with really big numbers in it. So let's move everything to one side, and then let's see if we can't try to reduce everything down. So I'm going to choose to move everything to the left side. Even though there's only one thing here, if I move this guy over, then everything's negative, and I want to avoid negatives. So I'm going to move everything to the left side. And when I do that, 1684 minus 1044 leaves me with 640x squared. Then the linear term becomes positive when I move it over, so plus 8640x, and then the constant becomes negative now. Now, looking at all of that, we can definitely take out a factor of 10 because all of them end in a 0. They're all even, and if you keep digging, trying to find more and more factors, you'll realize that 320 actually divides into all of these. So that's what we're going to take out. And when I do that, I'm left with a pretty simple quadratic function after that. Well, not super simple, but definitely better than what it was. So we get 2x squared plus 27x minus 405. All equals 0. So that coefficient, 320, that GCF that we factored out, I can actually divide out and away. We don't need that anymore. It plays no relevance to us in solving this equation. And again, just to keep in mind, we've been doing this part for what feels like 14 hours or so. This is all in the process of trying to find those critical numbers where this derivative equals 0, okay? So don't want to lose sight of that part of the process or what our goal is. So now we need to try and factor this guy if possible. This does produce some really big numbers. If we multiply AC, we get negative 810. So we look for factors of that add to make 27. And in this case, I think we get 18 and 40, or excuse me, positive 45 and negative 18 would make negative 810 and 27. So if we jump to our box, 2x squared, 45x, negative 18x, and negative 405. Hope I did that correctly. If I take out an x from both of these, I would get 2x and 45, and then that leaves me here with negative 9. So our final factored form of this would be x minus 9 equals 0, and then 2x, my tablet wants to freak out again, 2x plus 45 equals 0. One of these produces a negative 0. The second guy produces a negative answer to the equation, so we don't need to worry about that one. But this guy produces x equals positive 9. So we have our critical number now, x equals 9. So now what we have to do now, if this was a previous problem, we would take our critical number and now we would decide between first derivative test or second derivative test to decide whether we've got to, or confirm what we suspect to be true, which is having a relative min or max. In this case, we're hoping that it's a relative minimum. However, for this guy, this one's special because the variable x is what we're testing or looking at for the min or the maximum, but that variable is kind of pinned inside of this interval. There's an implied restriction on the possible values that x can take because this distance that x lies within is fixed at 30 feet. So the smallest that, or the interval that is trapped between is 0, 30, but it's non-inclusive. X couldn't be 30 because otherwise the cable would be like right up against at the base of one pole, and the poles would fall. That one pole would fall over. So we know that it can't be 0 and it can't be 30. It has to be something local in between. So when we are finding extrema with a given restricted interval like this, what we are actually doing is finding absolute extrema. So it becomes a special little scenario here. So what we are essentially trying to find is the absolute minimum in this case, because we want least amount of wire on this interval. So to find absolute extrema, remember this is where we're checking endpoints and critical numbers that fall within the given interval. So we would check or create a little chart. And again, this would just be values of W, not the derivatives. We're not looking at increasing, decreasing, or concavity here. We want to know which of these possible values of X produces the minimum or the least amount of wire used. Is it when X equals 0, 9, or 30? So to do this, this would definitely be, you would need some kind of calculator because we're going to plug these values of X into this form of the primary equation. So it's going to take a little bit to actually substitute those in. Now, plugging these values of X in, we can use a graphing calculator to help us speed up the process. So one option, whenever you're repeatedly plugging values into the same function over and over again, I recommend storing the function into y equals. So I'm going to do that here real quick. So y equals would be the square root of x squared plus 144. And then get out of here. Older calculators, make sure you close the parentheses after that 144. And then plus square root of the second guy. So the reason why I'm doing this is when you have a function stored, you can easily pass multiple values of x into that function in a couple of different ways. So now that I've got this guy. So one option is to go to your table. So if we make sure that our table is on ask mode, then when I go to second graph to look at the table, delete all these guys, get these out of here. Now we could just plug in whatever values of x I want to substitute in. So 0, 9, and 30 evaluates them pretty quickly for me. Another option is using the variables notation. So if I go to the vars menu and over to yvars, and we choose function, and now we put our equation into y1. So if I choose that guy, and then in parentheses, I can type the number that I want to substitute in there right after, and it will evaluate that. So then I can just recall that text back up, then we can change it to 9, and then one more time, then I can plug in 30 at the end of my interval. So that's the idea. So whether you want to do it with the table, or you can really sit there and hand plug in the all that calculation. But if you're doing it repetitively, it's just faster to make the calculator do all that for you. So out of those three values now, let's copy these down onto our chart. So when x is 0, there's 53 point, we'll call it 0.04 feet of wire. When x is 9, there is 50 feet of wire used, and when x is 30, there is 60.31 feet of wire. So obviously, out of all of those options, when x equals 9, it is in fact the absolute smallest value for w on that given interval. So that would be our answer. Let's just make sure that we didn't need any other questions. So yeah, so in this case, we are just looking for where the stake should be placed. So it should be placed 9 feet from the first pole. So this side should be 9 feet, and then this side should be 21 feet. So again, this one was definitely longer, more work involved, more steps, but the process didn't change. It was more difficult because of the extra equations with the secondary, and really just the fact that they were radicals. It makes everything a little bit more difficult. And finding that critical number was definitely more challenging for this one, but they're not all going to be like this guy. So don't get defeated or too anxious about that. Set up each problem with the same mindset, same thought process, and make sure you've got your primary and your secondary equations.